anywhere except for breaking out the sense of okay, that's actually super cool, and I want to. So I might add a couple more sentences. I'll send you the final file back to you. Yeah.
Okay. So I hope you're making good progress on malloc. I know for me, the first time I ever implemented a memory allocator was sort of an eye-opener to think that you can just write regular code and suddenly you're doing things that are, you thought some magical, mysterious part of the system was doing for you. And you see that it's all not easy to do, but not conceptually straightforward. So today we're going to move on to what I think is one of the really interesting parts of this course, especially relevant in this era when we have all these multi-threaded processors that allow us to execute multiple programs simultaneously, and because so many machines are hooked up to real-world devices that require some kind of asynchronous control, that you can't predict when events will come in from a camera or a network or a mouse or some type of sensor. And so you have to, the processor has to just be ready to jump and handle any of these different events. And one of the best ways to do that, and so that brings into the idea of concurrent programming, meaning having a computer that can do more than one thing at a time. And this is actually a pretty tricky business. The many bugs out there in the real world have to do with concurrency errors. And it's partly that there's a couple of things behind that. One is that it's just really hard for we as humans to imagine all these different events that could occur and what order they might occur in. And often you can anticipate, you'll think, well, I'm first going to read the camera and then I'm going to pick up this information and then do that. But instead, the events happen in a different order and you're not really ready for that. And it's even difficult to test out these things because it's hard to set up real-world scenarios in which the event orderings vary over their full range of possibilities. So this is an area where you just have to, and there are tools that can help you, but at some level you just have to be much more careful about how you write your code. You can't just think, oh, I'm going to just throw some code down, start running it, figure out where the bugs are, patch them up, and then ship it. You really have to be much more meticulous in your design. So there's some sort of terminology that there's some kind of interesting ways you can illustrate these. One is the idea of a race. So a race is basically any time there's two different entities trying to use the same resource at the same time. And if not handled properly, bad things can happen. So, but it's the idea of contention, that there's two different events that can occur and they might occur and they're both contending for some resource, in this case a parking space. There's also a lot of these ideas, by the way, you can illustrate with real-world examples as we see. The other is the idea of deadlock, and the sort of traffic intersection gridlock is a perfect instance of that. That you'll see that this intersection is blocked because each, let me see if I've got this, oh good. Each of these cars in the middle of the intersection is sort of preventing another car from getting through. And you can see actually very clearly illustrated a circular dependency that one has a resource, meaning this little piece of the intersection that this car needs, and so forth, that dependency. Each one has a piece of the intersection that another car needs, and they can't go anywhere because they all have this sort of circular cycle of dependency. And that's a classic deadlock situation. And so actually it's pretty interesting. You remember we harangued you that you can't use printf in your signal handlers. And we only were able to vaguely explain why. But now that you have this idea of concurrency, actually it's a perfect illustration of why. And the reason is that within the printf code, and we'll get into this later in this let's see, next lecture, I guess, the idea of locks. So lock is the way that you can sort of grab a resource and say, I have exclusive control over this. No one else can get to it until I say so. And so you acquire lock. You can hold that as long as you want. You can do whatever you want then if now you have sort of exclusive use of what a resource you're protecting with a lock. And then when you're done, you release it. And that will allow somebody else to acquire. And meanwhile, if 10 other programs are trying to acquire this lock, they'll just hang there and wait until that lock gets released. And then there'll be a sort of free-for-all of which one gets the lock next. But it's guaranteed that exactly one will get the lock the second time. You never have a case where two programs can acquire a single lock. So printf wraps locks around some parts of the code because it actually buried deep, deep inside in these obscure corners that have to do with time zone management, believe it or not. There's some shared resources, some shared global variables that if you had different instances invoking, they could possibly mess each other up. And my understanding is it's sort of, this library was created years ago when they weren't thinking about the need for sharing or concurrency. They put in this sort of unintentional shared resource. Nobody's ever done the work to pull it out and make it truly safe. We'll talk about how you can do that. And so instead what they've done is just slap locks around the whole code so that when you call printf or sprintf or any of those related functions, it'll first acquire a lock. It'll then execute whatever this code is that has this shared resources, and then it will release it. But here's the problem with the interaction with signal handlers. That imagine my main program is chugging along, and it decides, oh, it's time for a printf. And so it will acquire this lock and start to do something. And imagine right after that lock gets acquired, a signal comes in. And that signal calls this signal handler, and because the signal handler has a printf in it, printf does what printf does. It tries to acquire a lock. The problem is it can't get that lock because the lock belongs to the main program, and this program can't release the lock until the signal handler exits and returns back to the main thread, the main execution. And so it's a classic deadlock, although it doesn't involve 4 cars in an intersection. It's just two executions, even though they're actually all part of one process, that are sort of waiting for each other. The signal handler is waiting for the lock to be released by the main program, but the main program is waiting for the signal handler to return before it can release the lock. And this is a relatively rare thing. And so 99.9% you'll see, and you might have done it, and you got dinged style points if you did, you can throw a printf in a signal handler and it seems to work fine. Whoops. Shoot, I didn't mean to do that. But just to be perverse, we sort of purposely wrote some code that would sort of slam as hard as it could on this particular feature and see what happens. And so you'll see here's a classic case then that we're forking, we're running through a loop a million times, and each time we're forking a child and the child exits immediately. And of course that will then cause the sigchild signal to be delivered to the main program. And then the main program has a printf, and the parent has a sprintf followed by printf. And for reasons I don't know, if you just make it all a single printf, it doesn't seem to cause any problems, meaning I can't trigger this problem. And then you fire up this code, and it will chug along, and just whiz along, but at some point, it'll hang. And in this instance, it hung at somewhere close to 6,000, and other times it will hang, it'll be 50,000 in. So, and you can see this is sort of the worst case scenario in terms of I'm just doing signal handler, signal handler, signal handler over and over again. But it will hang. I've never seen it get anywhere close to 1 million before it goes. This code, like all the code for lectures, is sitting in a class AFS directory if you want to poke it yourself and try it. But I think you'll find it pretty reliably causes a deadlock. So that's the reason why you shouldn't put printf in a signal handler. But it's an interesting interaction between the sort of model concurrency that's created by signals, which is this sort of bizarre thing where main program's just executing happily, and then kaboom, a signal gets delivered, a signal handler gets invoked. It's all part of a single process. This isn't multi-threading, but it interacts with a feature that was added to printf to deal with multi-threading, which is what most modern processors support. Some of the students made the observation, actually, if every time you use printf, if you block all signals, if you sort of wrap around printf, just like we wrapped locks around it, if you block all signals before you call printf, and then you restore the signal mask to what it was before, that actually will work. But you have to do it not just within the signal handlers, but every place in the code, because the problem isn't really the signal handler. The problem that's causing this, really in the first place, is the main program. Make sense? And then there's other sort of, so deadlock is a classic, and when it happens, obviously it's a really bad thing because the whole system, or at least a good chunk of the system, is unable to make any forward progress. There's other ones that are more subtle. There's one that's often called starvation. And the idea is, imagine we have a busy highway with these long streams of cars going by. And in this crossways, we have yellow cars, and just by convention, that they basically have a yield sign. So they have to wait until there's no traffic on the main highway. And so they could wait forever if that green traffic just continues, and the system isn't deadlocked, meaning progress is made. The green cars are going just fine. And it's not an instance of one car versus another. It's effectively the stream of green cars that's doing that. And you can get that, you can imagine in a sort of process scheduling environment where there's two levels of priority. And you could have the high priority things always winning out over the low priority. Back, it used to be flying airline. For a while, the pilots and the flight attendants got to jump into the line in security ahead of regular people, which really was irritating. Because if you're waiting in line, as you know, you don't want to wait any longer. So that's an instance, and if there were an unbounded number of flight attendants, the rest of us could have been starved in the security line. So anyways, there's sort of these classic problems that arise. As I said, there's races that if you're not careful, you can sort of mess things up, and we'll show examples of that. Not as glamorous as crashing cars, but where your program is definitely not doing what you want. We saw deadlock where the whole system freezes up, or various forms of starvation, or sometimes talk of fairness, where due to some service can't be provided because something with higher priority keeps winning out. And so this course is really just, in this course, it's just the beginning of a discussion about concurrency. There's other courses that spend a lot more time on it. In particular, if you take 214, spends a lot of time in concurrency, and other courses on campus in various ways do a lot more in concurrent programming than we'll get into. But it's a pretty important thing. It's sort of fundamental. So just as an example, you might, in the network programming, you went through an iterative server. And the iterative server does fine, meaning it lets a client make a connection and then run a session that involves sort of a cycle of sending messages back and forth and reading them. But there's a weakness in this server in that it really can only handle one client at a time. So for example, I've got the server fired up on Hammerhead Shark, and I can use it to echo things. Even misspelled, and it works fine. But if any of you, if you guys have a laptop handy and want to jump to the course, the code for today, it's in do you know how to get to it? The course AFS directory /www/code/23-concprog. And if you type in this prompt, echo client, you give the host is Hammerhead Shark, and the port number is 15213. Give it a try. Anyone trying it? Anyone trying it? But you'll be locked out because I've got sole access to the server. The server has the weakness that it's only able to do a single client at a time. And as long as I'm maintaining my connection to it, I'll dominate it. But now if I exit with a Control D, somebody else from Kaiser Panzer was able to get in and is starting to do the echo. Who's that? Okay. And now if you hit a Control D, no one else trying? Where's your sense of adventure? There you go. Kaiser Panzer is back. Anyways, you get the idea that this isn't a very good server if you were Google and you had 1 million customers, but you could only do one at a time. So let's make sure we understand why it's really only able to do that. And so the way this will diagram is, and this is a common way to show protocols involving concurrency networks and things like that, is time is going down, and each vertical bar represents one thread of execution, one process, think of it. And so if you recall, the overall idea is that there's a server that's sitting there running in listen mode. A client makes a connection request, and then the server accepts that, and then the client is able to start echoing by writing to the server and reading back what it returns. And it can keep doing that, write, read, as long as it wants, and then it closes the connection. When I hit Control D, it closes the connection, and that was that. So meanwhile, if another client comes in, like Kaiser Panzer did, and wants to make a connection, they can connect to it. And interestingly enough, and it's a little bit subtle, the call to connect actually returns, even though there's no connection yet. A little weird, but that's the way it is. I'll explain it in a minute. But then when it starts to try to write, that call will hang up because there's nothing to write to. There's no actual connection yet. And so it will basically get stuck there in that part of the code until this other connection is closed and the server is able to now accept another connection. I'm pointing to the screen that you can't see. But anyways, it sort of sits there and just hangs for as long as that other connection exists. And like I said, the slightly subtle part is the client code makes a call to socket, which just sets up this the data structures for a connection. It makes a call to connect to a server. That actually returns, and then it's this call that blocks. And it's a feature of, a slightly subtle feature of TCP, the network protocol, that it will return from connect even though it doesn't have a connection. Partly as a way to sort of speed up once a connection is formed, then more quickly moving on. But whatever that particular feature isn't really important here. It's just a little thing you might notice. But the point is that the second client is blocked. It can't do anything as long as the first client is connected. And so that's a flaw. So this is clearly a case of a concurrency. We need a concurrent server, one that is able to manage multiple connections at a time. And we'll discuss in detail 2 different ways of doing this and sort of give you a little overview of a third way. So the first way is to simply use the machinery you've already learned about processes and forks, and basically fork off a new process for every connection. And that's, like I said, you can understand that exactly using just the ideas of fork that you know already. There's a second type called an event-based that we won't talk in much detail. It's covered in the book. It's pretty interesting. I'll just sketch through it. And then there's a third, which is really where we want to get to today, which is threads. And you've heard this term threads. We keep mentioning threads over and over again. Finally, today, we're going to start talking about what threads really are. So the simplest then is this process one, that basically the server, when it gets a connection request, will accept that connection, but rather than handling the echoing itself, it will fork off a child that then manages that particular connection. And the echoing will go back and forth this way. And meanwhile, the server will be able to continue looping around and accepting new connections. And so if a second client comes in, again, it will fork a second child to manage that connection. So the main thread of control here of the server is only a loop to accept connections and to fork off essentially a handler that can deal with whatever that connection needs. So doing this there's a few little subtleties in doing this correctly that let's go through. So this is the code that was presented last week of the iterative echo server, the one that we just demoed. And so again, this is the server. So the loop here is that it's accepting a connection, and then it's managing that connection, the reading and writing, and then it's closing that connection. Well, we've got to move things around a little, but what we'll basically do is put the echo part into a child. So we'll call fork, and when the side that returns 0, of course, is the child, and that will be responsible for both the echoing and then once the connection is done, to close that file descriptor. And this actually makes use of a feature of the accept, that it lets you deal with different file descriptors, essentially different ways of connecting. So the listen file descriptor is the file descriptor that's accepting new connection requests. And when accept returns, it generates a new file descriptor that is the actual, the specific connection that's been created for this particular client. And by having those different, then we're able to do this trick of now I can just run accept on that same listen file descriptor and use, I'll generate a new connection file descriptor for every time I return from accept. There's a few subtleties about closing file descriptors, closing files, because remember that when a fork occurs, both the child and the parent have copies of the same file. All the open file descriptors are duplicated between those two processes. And so it's very important that the main program close the connection file descriptor. Otherwise, if it doesn't, you think about what it's going to do is generate a bunch of orphan or unclosed files that will actually grow unbounded, which is not good in a server. So if it doesn't actually actively close that file descriptor, then remember, files only really get closed when the reference counts get set to 0, and that will never occur for any of the connections that are created until the program exits the server. But remember, server in principle should be designed that can run forever without abusing or overusing any resources. So that one's pretty important. Similarly, the child has to close the listen file descriptor just for the same reason. It's a little less critical because we've designed our children to only manage one client's worth of echoing, which presumably won't go on forever. So it's a little less fatal, but still you can imagine there's no inherent bound on how long the client stays active. And so that wouldn't be a good thing, but it wouldn't be as bad as the other one. But in any case, the right thing to do is to close the file descriptors that aren't going to be used by this particular process. So that's one of the tricky things. And again, as I mentioned in concurrent programming, you often have to be just scrupulously careful and not rely on just running code and seeing if it crashes, because it's really, unless you ran this for a really long time, I mean, usually I think most processes can support 1,000 or more open files. The likelihood of you encountering this in testing is fairly small. And then just to really do this right, we should avoid zombie children as well. And so we have to create a SIG-child handler that's the type you've used that will call waitpid and be able to reap all the children. And again, this is an instance where this is pretty important because the server could run forever, and therefore, if it doesn't do this active reaping of its children, it can have an unbounded number of zombie children. So again, conceptually this is straightforward, but actually there's some subtle points in implementing this kind of code that you have to be careful about. So just as a sort of picture, remember this important distinction between these two file descriptors, that I make a connection request, the client does, to the listen, and on the server side, that client request comes in to the socket that corresponds to the listen FD that was created and passed to the accept call. But then accept returns a second connection file descriptor for this process that then becomes sort of owned, so to speak, by the child that I forked off. And then they sort of, the server and the client then have a session where they can go back and forth, reads and writes, to send messages back and forth. So the overall model then is I have this pink box represents the sort of main server that's just in this loop creating new connections over and over again. And that each time I get a new client, I'm forking off a new process and letting that run. So in this instance, this is a perfectly fine implementation. There's a few things, though, that make it not ideal. One is there's a significant cost and overhead of fork and processes that if you did a lot of this and it wasn't just echo servers, but something more serious, you'd use up both time and resources. But more seriously is, if you want to do any kind of interesting application, like more than echoing, it's very difficult to share information between processes. There's no sort of common state to them. They, as you know, part of their trick is that they, at least conceptually, duplicate and create sort of completely independent state. And so if you want to like have a database that of customers, you know, that all these servers are managed, or any kind of shared information, it's not easy to implement using processes. You can do it, but it's not easy and it's not very pleasant. And then, as I mentioned, there's these slightly subtle points about this sort of shared file descriptors. But the biggest problem is it's really a pretty limited model of what you can do with this model. So anyways, just some pros and cons. It's a very relatively simple sharing model. There's some subtleties, but relatively speaking, pretty easy. But as I mentioned, it's not very rich in terms of possibilities. So then there's the second part, and we're not going to really talk about it much, but those of you who do network programming will want to learn this. There's this whole set of library code that lets you manage what they call manage events on sockets. And there's a class of functions that are called select to do that. And so roughly, and the idea is that this isn't actually concurrent programming at all. What it is it's a way to, the problem I have is if I were to just try to do this all on my own using file descriptors, and every time I made an exception, a connection request, I could accept it, I could create a new connection file descriptor, I could put it in an array, have as many connection file descriptors as I had clients, that's fine. But then you're sitting there going, okay, now what do I do? Should I listen for a new request? Should I see if one of my clients has some messages that they want to be sending me? If so, which one? How do I know? Well, the idea of I/O multiplexing is basically that you can create this array of all the file descriptors that you're maintaining. And then there's you set a mask to say, I want to see if there's any traffic, any incoming information on any of these connections, any of these file descriptors. And if so, tell me which ones are there. And so you can go ka-chink, run this function called select. And select will, if there's no incoming input on any of these file descriptors, it will hang. But if there's one or more, it will give back a mask saying which file descriptors have data that you can read. And so this works for all file descriptors. The file descriptors corresponding to network sockets, which are network traffic, including the listening file descriptor and any client file descriptors you've created. But it will also be for terminal I/O, for reads that you're making of regular files. So actually, there's quite a few possibilities. And then your program can then just pick through this array and say, oh, okay, there's a new connection request. Let me accept that, and I'll stash the, create a new connection file descriptor somewhere in this array. And you say, oh, there's an input from this client here, and so I'll read that and echo it back. And oh, there's input from these other two as well. So it actually is all purely sequential code, and in some ways easier to think about, but it just does this trick that is sort of integrated into the whole file management system and socket management that says, at any given time, I can sort of query and ask, which among this set of file descriptors has input available? So it's a nice simple model and relatively easy to work with and debug. And so that's good. It turns out that there's some weaknesses. You'll find, for example, if I did this in this case, and there's code in the book that does it, but it has this sort of security weakness that if one of the clients passes in a string that doesn't have a end of line character, the server will hang up on that line because it's waiting. It's an echo. It's not echoing character by character. It's doing line by line echoing, and so it will just hang indefinitely. So, nice clients don't do that. But in the world, as you know, there's many bad actors out there, and so increasingly people write code that is not making any assumptions about the reasonableness of clients. And so to actually then do, you'd have to change the code in your echo client to do line by line, basically character by character echoing or something like that to deal with it. And this is a problem with servers that are implemented this way, that they can be vulnerable if you don't sort of handle all the possible behaviors of clients. And the other is, in this modern era, most processors have multiple cores, and this code is running, it's totally single-threaded, and so it's not taking advantage of these computing resources it could have. Excuse me. Okay, let's jump into a quiz. This is a short one. Okay, I think we're good here. And I think you guys mostly got the right answer. So, yeah, we just saw starvation. Remember, the car is on the highway. And so the point is, in starvation, something is making progress, but others are not. And then malloc, this is very important, that your fit algorithm and all your segregated lists are really mostly going to focus on external utilization. And to get a good score on this, you also have to deal with internal fragmentation. So, good. Okay, so now you've seen the lead up of, let's talk about what I kept promising we talk about, which is threads. So this is an interesting way of thinking about it, that we've sort of talked about, when we talk about programs so far, we sort of say there's this whole bunch of stuff that's in memory, and that includes shared libraries, global data, the heap, but we also say that the stack is sitting there in memory. And so that's sort of the data associated with the program. And then there's the other part here, which is sort of what defines this particular process. There's all the registers, including condition codes, stack pointers, program counter, and then all the various data structures that are maintained for you by the operating system kernel. And as we saw before, those are kind of mapped into the same address space, but up in regions of the address space that you don't have access to. But what we're going to do now is sort of rearrange that picture a little bit through the magic of PowerPoint and say, let's think about the stack as really part of the runtime control for this program, because the stack is also the history of outstanding function calls, and all the data on the stack are pretty important. This sort of defines where within the program the execution is taking place and what to do as the procedures return. And then we'll just sort of push all that. Remember that all this kernel stuff is in virtual memory. And in some ways, it's just there being managed for you by the kernel. And so you don't have to think about it too much. And let's call that first part the thread. In this case, a single thread. The combination of basically the registers plus the stack. And now with multi-threading, the idea is, okay, if you have one thread, why not two? If you have two, why not three? Why not have a bunch of these threads? And the key idea here is each thread has its own execution information, but it's sharing the sort of more global information. It's sharing the code, just like we saw with but it's true sharing. It's not creating replicas that then go off and diverge. It's actually keeping all these threads having access to the same global information, including the heap and including the global variables. So the stacks are private, and we'll have copies of the registers, but so it lets us now run within a single, this is officially still considered a single process, but there can be multiple threads of control, each doing their own thing. And we saw with processes that there's this sort of hierarchy, a tree structure, the way forks and childs work, there's parents, and so it forms this tree. Threading, at least the model of threading that we use, are sometimes referred to as peer threading, meaning all threads, even though there'll be a main thread and it will create new threads, and those threads can create other threads, but at some level they're not, one is no more sort of special than the other. There's no notion of this hierarchy and so forth. So all these threads sort of have equal priority and access and privileges. And once again, we'll talk about this idea of concurrency. We'll just say if two threads sort of have overlapping executions, then they're considered concurrent. And we'll actually now, if we only had single core processors, then we'd have to just basically emulate this concurrency, meaning that we'd just jump from one thread to another and sort of make it appear that they're all being executed, even though at any given time only one is. But nowadays, on a multi-core processor, you have the possibility of truly running on separate cores within the same chip these different threads. They'll each have their own registers. They'll be accessing the data. It's all mapped into virtual memory. It's all one system with its own set of page tables and resources and things, all managed by the kernel. but they all are, so they're sharing the sort of virtual address space, but they're each executing their own. And they'll have their own stacks, and the stacks are actually still part of the virtual address space of this process, but they're just, instead of having a single stack in one part of virtual memory, we'll have as many stacks as we need. And we know that stacks are bounded. We always cap how big a stack can grow, so we can just allocate, I think typically about 5 megabytes each for each of the runtime stacks we want to have. So you see the distinction then between what we saw with processes via forking versus threads. That in some ways they have some similarities. It creates multiple threads of control, most sort of execution, logical flows running concurrently, and the processor and operating system have to somehow manage the scheduling of those. But they're different in that the sharing is true here, as opposed to sort of, remember we saw with processes that we at least give the image that we're replicating. We're making independent copies of the whole address space. In general, threads, the overhead of scheduling them and managing them is less than a process. And you can see why. When I create a new process, I have to set up all the VM area structs. I have to sort of mark all these page tables entries as being set up with so that they'll be replicated if I try to do multiple writes to them, and all that stuff. Whereas here, all that junk is taken care of. All I have to do to create a new thread is set up a stack, small amount of data structure, and then I can start running it. So the main way we'll make use of threads, in every language, there's many different ways to do threading. And some languages like Java, Python, so on and so forth, most modern languages, have a built-in threading capability. C doesn't, nor does C++. And so instead there's this external library called pthreads, P standing for POSIX, which is sort of basically back when there were multiple variations on Unix all being created by various different companies and organizations. They all gang together and say, hey guys, let's come up with a sort of universal set of minimum standards called POSIX, and we'll all guarantee we support at least that aspect of Unix. So anyways, pthreads. And pthreads is this giant library, 60 functions, inscrutable arguments, man pages galore, all the usual stuff. But the basics of it are actually not so difficult. So this will be just to give you the starting point. And like in a lot of places, any library, you start with hello world, and it's like the ugliest code you can ever imagine, because you're trying to do something very simple with a library that, for which this is sort of, has a lot of machinery that we won't really use. But the basic idea of it, what I'm trying to do with this code is create a new thread whose only job will be to print hello world and then exit. So I'm actually going to, my main's going to spawn a thread. That thread's going to print hello world. That thread will then terminate, and then the main program will figure out that the child is this other thread is terminated, and then it will exit. And so basically I will create, this pthread create is the function that spawns a new thread. And pthread join is sort of the wait PID of the pthread world. It waits until a specified thread has exited, and then it continues on. So there's a few things going on. In pthread, you pass the first argument is a pointer that then gets filled in by the library with the ID of the particular thread that was created. And thread IDs are like process IDs. They're unique numbers to identify it. There's many arguments you can pass to a lot of these functions that you can just set to null if you don't really care. There's some special attributes you can assign. The thing that's the most important, the two things that are the most important is what you do is basically pass a pointer to a function. So it's a little like a signal handler that you pass except that we're not waiting until the signal happens here. We're just right away going to fire up this new thread, but this becomes the thread routine. And then you can pass in an argument that then becomes the argument of this thread routine. So in general, the thread routine then will be a program that is given a single void star as a pointer, and that will be whatever was passed to it in the create. And that void star then you can cast to whatever you want and extract out of it. You can pass a pointer to an array, you can pass a pointer to a struct, whatever you want, and then that can be sort of deciphered by the thread function. So passing around void stars, as you know, the way in C is the way of sort of creating generic arguments. It's not very elegant, but it gets the job done. The C's version of polymorphism, you might say. And then the pthread join, when it will pick up, you'll see that the thread gets to return a void star, and pthread join then will can get a copy of that if it chooses. So the point here, though, in this particular example is I called pthread create, that created a new thread, and pthread create returns right away as soon as this new thread is created. And then the main thread called pthread join, and then it just would sit and wait until that particular thread terminated. And then the newly created thread calls printf and returns, and then when it returns, it gets essentially reaped, although that's not the right term for threads, and the join will return. So that's sort of the simple version of a pthread program. Okay, well, why don't we try something a little more classy than that? And this is the code. And it's got some really interesting parts to it. Interesting if you're a nerd, which I am. So that works. What I want to do is, you remember that I want to, I'm going to want to create a thread for every new client that contains enough information to it to be able to do an echo back and forth, which is actually, if you think about it, all it really needs is the connection file descriptor. Because remember, threads by definition share all the file descriptors because that's part of the global data. But here's the interesting thing, and we'll see this, that I'm going to call malloc here. And you'll see there's no free in this code. So somewhere we better look and say, oh, there better be a free somewhere. We'll check that out. So I'm going to malloc a copy of an int's worth of storage, which might seem kind of silly. And I'm going to store in that place the connection file descriptor returned by accept. And so you notice I call it confdp for pointer instead of just confd. So confdp, its data type is here. It's a pointer to an int, not just an int. Okay? And then that's the argument I'll pass to the thread routine. Remember, the thread gets a void star pointed to, and I'll just pass the pointer to this. So basically, I've created this little block of storage that confdp points to, in which the actual connection the file descriptor will be. If you can read that, good for you. And then I'll pass that pointer then, and the thread will have access to that little block of storage. And we'll find out very soon why I did it that way and not some more straightforward way. And here's the thread routine. So here you see it's able to then extract out of that block. It can dereference that pointer, casts it to an int star, dereferences it, and gets out of it the connection file descriptor. And you can see down here, it's going to use our standard echo and close on that to manage that client. But it's also going to do a few other things. One is it calls a function called detach. And there's two different thread types that are supported by pthreads called joinable and detached. So joinable is what I showed for Hello World, that the concept of it is that a thread will be created and then somebody's going to wait until that thread is finished before proceeding. It'll join. A detached thread is more like one where there's something that will happen. I don't care. I don't even care when it finishes. It can run forever as far as I'm concerned. So just detach it and let it do its own thing and never bother me about it again. So pthread supports either model. So I told it, use a detached thread here. And then here's the call to free. So you can think of this as sometimes referred to as a producer-consumer model, that the server allocated via malloc the little 4 bytes worth of storage needed to store this file descriptor, passed a pointer to it, to the thread consumes it, and then says, don't need it anymore, and can call free. So malloc should always be balanced by free. Usually you put the free in the same kind of, whoever created it should free it, but in this case it's a producer-consumer. And let's see a little bit why we did what seems like this very awkward thing as far as passing that argument. But first of all, you can see the overall model here is very similar to the process-based one, that now our server is just going to, every time it gets it will just be in a loop, accepting new connections, and every time it gets one, it will spawn a new thread, and that thread will be responsible for that client, and then when they're done, that thread will just exit, and nobody cares. We won't pay attention to it anymore. Right? So it's a little like the process, except we didn't do any waits. Question?
What's the difference between a detached thread and a process?
A detached thread is still a thread. It's still, we don't really use it here, but it's running in the same address space as the original. You know, a fork, it conceptually makes a copy of all the memory, and now as the parent and the child, make updates to global variables, those will be independent. But within a thread, if there's global variables, that will all be the same. So it's the difference between a thread and a process. Yes?
So if a process is terminated, no matter what the state of the threads are, they'll all be like done?
Actually, it's an interesting question. If any thread, the main thread or any thread calls exit, then the whole thing goes kabong, and they're all done. But if a thread returns, or it calls pthread underscore exit, only that thread will terminate. So I believe that the main program, though, yes, if you return from main, it will return back up to a function that we'll call exit. So if the main program either calls exit or hits the end of it and does a return, then the whole thing's over. But if it runs forever, like a server would, then there's nothing going on.
Threads in one process communicate with threads in another process?
No. Think of processes as like a pretty strong firewall around them. There are ways, you can create pipes between them, network connections essentially, various ways you can set up communication between processes, but it's not a normal thing. But whereas within a process, the multiple threads by default are able to talk, interact with each other in all kinds of ways. Good? So yeah, it's the difference in processes. Sharing is possible, but hard. With threads, sharing is so easy that you can have a lot of bugs because things tromp on each other in ways you don't want them to. So which way do you want? It depends on the context. Good? So like I said, there's this difference between joinable or detached threads. If you don't call detached, then you've got to join it or you'll have the equivalent of zombie children, except they're zombie threads. But if you detach them, then the creating thread, the main thread, doesn't have to worry about them ever. That once they exit or once they return or call pthread_exit, the system will essentially reap them. Okay, so now let's talk about why I went through that rigmarole about mallocing in one place and freeing in another and passing a pointer and blah, blah, blah. Why did I do that? Well, let's imagine we did the more obvious thing, which is we just have a local variable called the conFD, and we pass a pointer to that, to the thread. And then the thread can happily, it's a perfectly good pointer, it can dereference that pointer and extract the connection file descriptor out of it. But if you think about it, what that means is this local variable will be on the thread, on the stack, of the main thread. And we'll talk about this next time. There's actually, one of the weird things about threads is it's perfectly legal to have references between threads, between the stacks of different threads. It's possible and it happens. So that's not inherently a bad thing. The problem is that let's just assume that this connection FD is at the same location in the main stack throughout the life of this while loop. The problem is if I then create a second thread, then I've set up a race condition because I'm hoping that the first thread will read out of this pointer the connection file descriptor that it's supposed to use before my call to accept returns and overwrites that same local variable with a new connection file descriptor. Make sense? So the problem is that really this, you think of it, this memory location within the main stack is a shared resource, and I've created a race condition that I'm trying to assign a value to it, have it get read by a newly created thread, then possibly assign another value to it, have that read by a second thread, and happen. And it's purely a question of which one wins. If this child fires up really quickly and sucks that out, then I'm fine. But if for some reason the operating system decided to respond to this accept more quickly than the child can get created, then I could possibly overwrite it. So just to demo it, you'd have to work pretty hard to create that particular race in this code. But just to show you it, the same idea is some sort of very simplified code that does basically the same thing. What it does is it creates 100 threads passing the same pointer to each one of them, because it's a pointer to this local variable I in its own stack. And so I'm doing the exact same thing, except I'm doing this without any network stuff going on. I'm just going to fire up 100 threads in a row as fast as I can. But if you see it, I'm really passing the same thing to each of these. I'm passing a pointer to some place in the stack, and it's the same pointer every time. But I'm assigning different values to the variable that's stored in that stack position. And then meanwhile, the thread will extract this integer I, and it will save it in some place that I can basically build up a collection of all the different values of I that were passed to one of the 100 different threads. So if there were no races, then each thread would I'd get values 0 through 99 for the 100 different threads. But what can happen if this goes too quickly, then I can have basically multiple threads will see the same version of I going on. So this code, again, is on the web page. And so what you'd get then, this is sort of like a histogram of for each possible value of I, all 99, how many instances of those get observed by one of the threads. And so if there were no race, it'd be exactly 1. Even running on a single core laptop, which you might have trouble finding one nowadays, so this I did a while ago, you see that the race still occurs. There's a couple times when basically it gets around this loop twice before the threads have a chance to respond. And so there's a few cases where I'm seeing that like no one gets value 0, but 2 of them get value 1, and so forth. If you run it on a multi-core server, excuse me, it gets even worse. That you can see that in this example, there are actually 12 different threads that got value 90 out of this routine. Yes?
How are you able to avoid the race condition with malloc?
So that's an interesting question. So let's think about that. So what's it about malloc that makes this so special? Here you see that, so this is the same idea. I'm going back to the original code, not this example. That I'm mallocing an int, and then I'm storing my my file descriptor in that malloc location and passing a pointer to it. So malloc, by the way, is thread safe. So it has locks built into it so that multiple threads can call it. So it's good. And so you can think of it, each of these calls to malloc is creating a new and unique place in the heap for this. And so each of the time I call this, I'm actually passing different pointers here, right? And so I'm basically creating these isolated spaces for all these different ones. And then within the thread, it can say, okay, I've got it, and call free. And that storage can be reclaimed now and potentially go back and get reallocated again, but only after I'm absolutely certain I'm done using it, right? So I'm being very careful. It's sort of like this handshaking. I'm saying, okay, here it is. I got it. So it's setting up that kind of execution model where, like I say, a producer-consumer model where it's very carefully managing these and making sure it doesn't have the race. That make sense? So that's just a little, usually we discourage people from mallocing ints worth of storage, but this is a case where it's the right thing to do. More typically, too, what you're passing is a set of arguments. And so usually what you'll do is you'll define that it's some type of struct. And you fill it up. You'll malloc space for that struct. You'll pass it to the thread creation. The thread routine will then cast that to whatever struct pointer type it is, and then extract the various arguments. So that's a more typical model of how you use this. Yes?
Is there any reason you couldn't just free outside? Or,
well, you mean the main routine free? Yeah, see, but then there's a race. Right here, right? If I tried to free like here, how can I be sure that I've basically consumed? That's why you want to think of it as producer-consumer, right? That only after the consumer is sure it's done, then it can basically say, okay, all set. and you're not really communicating. You're basically just making calls to malloc and free to do this. But that's the idea of it. Good? Yeah, these are very important to really understand. So these are good questions. Okay, so we now have a pretty good idea of what threads look like. We'll go in more next time and the time after that and look at how you really do synchronization. This example is pretty limited, but we can see already that there's some very specific things we need to do. So one is, as I mentioned, threading, sort of sharing is the default, and it's hard not to share, and that can actually get awkward. There's no way you can look at threaded code, some global variable in threaded code, and know, basically, do I have to protect this with some kind of lock to be careful or not? It can be very awkward. And it's also difficult, we'll see, to actually test this code and run it, because the thread scheduler, you'll find that the Linux thread scheduler is not too clever, or it tends to be very repetitive, like it'll always give the child priority over the original, or something like that. You can run program 1,000 times, and it seems to just give you the right result, but it's because it didn't really try out all the possible event ordering. So you saw that example with where I could induce this sort of races, but I had to write code that would really bang as hard as it could at that particular feature to make that happen. If I'd written a more normal, like echo server without using the malloc, I probably could have gotten away with it, except maybe 1 out of a million times all of a sudden it would have a problem. And 1 out of a million's really not good enough in this world. So we'll talk more about some of those issues next time. Okay, so I guess the main point you can see where we're heading for is process-based concurrency is pretty limited and not that useful. Event-based, as I said, is actually, it says it's bad. Actually, from a programming point of view, it's actually a pretty easy model. Like, we'll find GDB is not your friend with threads. All of a sudden, you're going to start using printfs again. Because, I mean, there are support in GDB, but it's really, basically, when you say break here, it's going to say, well, which thread do you want me to break, right? So it's pretty awkward there. Whereas this event-based, which if you take the networking class, you'll get into this. It's all within a single loop, and basically it's like a little scheduler built into the code that you have much more control over. So anyways, that'll get us for today.